So we move now to the application of this inference time intervention technique. We look first at the engineering requirement verification. This is a work, as I say, done by my PhD student that developed also this head intervention technique in collaboration with XI, that is a student from the International Space University that provide us with one of the engineering models that we used. So if engineering or aerospace engineering is not your background, but you have to imagine that complex system when they are designed in the first phases of the design process, they are designed with what they're called the model-based system engineering tool. Capella is one of the most used. You have to imagine the complex engineering system could be a spacecraft, an aircraft, where all the design decision and information are stored in a tree-like structures that represents at the root you have the spacecraft, and then you have all the different subsystems with all the different properties and all the different values that come from the design of that system. So this is like a structural representation of the engineering system. You can see it as a tree, you can see it as a graph. And then you have the requirement that is in natural language. And when we did this work for Annalisa contract at the beginning, we just trained a LLM to, given the graph representation of the system and the requirement in natural language, to predict is the requirement verified or not. And since we're not steering any behavior, we got, let's say, equally good in both classes. So a lot of false positive and a lot of true negatives as well. But in an environment like engineering, a requirement verification, like we said before, false positive are unacceptable. You can't have an automated system that tells you a requirement is verified when in practice it's not. So that's where now we want to introduce these intervention techniques to avoid this behavior of, say, a requirement is verified when it's not. So the whole idea of this work is, first we have a whole part of the pipelines that deals with the Capella model that represent your system, the requirements. I kind of zoom in the Capella model to extract only the parts of the model that are relevant for the requirements. So we do that with cosine similarity, if you know what it is, and then we imagine it like we zoom in this big graph that represent the system to isolate only the part of the graph that are relevant for the requirements. And since we want to feed this in the prompt of LLM, we need to verbalize them, and we just verbalize them as triples of entity, relation, and entity. This is an example. In this Capella representation, you have the entity airlock that is in relation with is in the relation directly performed with the entity depressurize. So at the very beginning, when we were using just state-of-the-art, like I say, baseline large language model, you just feed in the prompt the verbalized part of the system that you are interested in, the requirement, and you just ask, does the system verify the requirements or not? And as I say, he had he was learning, but he also had a lot of false positive. This is just another slide that explains this verbalization of the Capella SysML system, where you have to transcribe it to text first. To demonstrate the efficacy of these intervention techniques, we use two models, a model for the moon base mission that was provided by the student at the International Space University, and the Hubble Space Telescope models that were just funded online. They're both Capella models, so they interface well with our system. They have a total of 76 requirements that we have either created or filtered to have a balanced data sets of requirements that are fulfilled and not fulfilled in both missions. And we keep 20 for each mission in these requirements as unseen requirements. So we use the remaining 36 for our intervention, so understanding which heads are the most important. And also we want to compare how that compares to a fine-tuning approach. The other thing that is interesting here is that the intervention, when we design our intervention techniques, we design it only on the moon-based system engineering model. So basically it learns the most influential heads to not promote false positive actions only on the system engineering model of the moon base. And then we'll see that it equally behaves well when we test it on the Hubble Space Telescope. So generalized well, not specific only to one mission. So the first things, as I said, in the general technique, we need to identify which layer and which head of our transformer model. Here as well was a Llama 2, I think, model, are the one that promote the behavior that we want to promote. Here, instead of looking at all the layers and all the heads, we did a bit of a smarter search. We call it divide and conquer, is a kind of tree search among the layer and the heads. And also we are optimizing alpha, that is the intervention strength factor. Why in the paper that we published with general technique, we were using the same alpha values. Here, if you pick more than one head, you can also specialize the strength to the heads that you've picked. So after this, let's say, smarter search of layer and index done on the moon-based dataset, requirement datasets, our metric is achieving 1 in precision. So that means there is no false. I'm always confusing. Yeah, that we are promoting the behavior of not having false positive. Again, the middle layer 13, 14, with the corresponding heads are the one, let's say, the top 3 ranking in our search, with the following strengths that are outlined here in the vectors. Another study that we've done is understanding how the parameter of the large language model, particularly the temperature, affect the strength of the intervention. So we have the top 3 configuration. So we apply intervention on layer 14 and 3 heads, layer 13 and 2 heads, and layer 14 and 1 head are the ones that are deriving from these studies of identifying the most influential layer and heads. We try different value of the temperature of the large language model and different percentage of the intervention strength factor alpha. And then we see how the precision and the recall change. So what's interesting here is that when you for all 3 cases, when you increase alpha, increase the strength, the recall decrease. So you are worse in predicting the other classes, but it's not the one of the false positive that you are interested in. And the other things that is interesting here is that for the 2 configuration that I have highlighted with a blue box, we have that when the strength increase, then you have kind of plateau of the precision. That's what you want to have, because you want to have perfect precision for your binary problem to ensure that you're not predicting any false positive. So these 2 configurations are the one that we keep for the subsequent studies. So we just see the layer 14 with the 3 heads or with a single head with a different strength. And then we compare how the baseline model compare in performances in terms of precision and recall with the fine-tune and with our intervention model. And we see that the baseline, as I say, has a precision of 56, 57, so a lot of false positive predicted in here as well, and a recall of 97, 95. While with our intervention technique, we are able to steer the behavior towards what we want, so perfect precision, 1 with 0 variance, with the self-consistency k equal to c. So this is a way of prompting the model more than once to ensure that is consistent, that is not there's no stochasticity in that, and it generalized well across both the 40 unseen requirements that are 20 in the moon base and 20 in the Hubble Space Telescope. So in this small test, our intervention techniques, let's say, outperform the fine-tuned model. And this is just some slides that shows in practice what this why picking these specific head and the specific layers is correct. If we look at the input prompt and the output of the model at the bottom, we'll say like the requirements that we want to test is a requirement that asks if the spacecraft shall ensure continuous communication with the Earth by utilizing dual antenna to broadcast and receive signal, and so on. And you see that the different color coded is the attention score, and you see that the attention score towards yes is highly correlated with the elements in the prompts that are highlighted with the blue box, that are the ones that are relevant for making that decision: communication, information from space, and broadcasting signal. So this is if you look just at specific head, and if you look at the attention score on the specific head and specific layer, that is the one that we picked for the intervention. If you sum the attention score over all the layer and all the attention head, you see that this kind of heat map is much more confusing. It's not as clear as in that attention head that we have picked, that is the one we believe drives the yes or no scores. So this kind of verify visually what we have picked and compute before. And this is an example of outputs after you implement this model. So on top you have the prompt in white. You have the requirement: the optical telescope module shall align its instrument with the focal plane to provide wide field imagery in ultraviolet, visible, and infrared light. We have the triplet extract from the graph of the Hubble Space Telescope, and then we have the answer. So the baseline model says that the final answer is yes, and that's wrong. And then we have the output of the fine-tuning and of our intervention. In this case, both fine-tune model and intervention gives the correct answer, that is no. But if you can read this with calm, because there's a lot of text, you will see that the reasoning of the fine-tuning is not correct, while our intervention technique provides us with the correct answer and the correct reasoning as well. And this is another example for, this is a requirement from the moon base engineering models, again with the corresponding information from the graph extracted and supplied to the prompt, and the comparison between the answer provided by the baseline model, the fine-tuned, and the intervention model, where baseline and fine-tuned model both answer yes on the verification of the requirements when the true answer should be no. So our intervention method obviously gets it correct because as absolute precision. So what's the key finding of this work? So well, this was already demonstrated in the general when we published the general methodology, but behavior of of this type of model can be encoded in sparse attention heads. In this case, one head, the layer 14 and 24, is the one we use to drive the precisions. Our intervention technique we propose is better than the fine-tuning on a small data set. We work with a very small data set, firstly because it's quite hard to find this type of data set. There are very much around there, and I think it's still valuable to show the existence of a model that works on such a small data sets. We can demonstrate that it's better than the fine-tuning on larger data sets. It was actually, if you remember the results on the AI coordination data sets, the fine-tuning technique was the one closer to our intervention model. And we have demonstrated that we can include fine-grained control action in safety-critical decision and environment. So this obviously has a broader impact in reliable spacecraft engineering in general. Can be an alternative method for fine-tuning when you have a small data set, as I said. Could also be used in conjunction with fine-tuning to even strengthen the precision of the fine-tuning methods, and it could be used as a framework for deploying LLM in safety-critical environments.